Hello everyone, and welcome to another GIS lecture video. And in this lecture video, I want to talk about this idea of errors in GPS. So in the previous video, we talked about this equation for GPS, and we said that we basically needed to know two things. We needed to know the time the signal was sent, the time the signal was received to calculate the time spent traveling, and that we could use that to calculate times the speed to calculate the distance away from the satellite, that we could then use this trilateration concept to figure out where 4 or more satellites intersected to figure out where we were. And this is a straightforward theory, but let's talk about what can go wrong and why GPS isn't always perfectly accurate. So I think the best way to do this is going to be to draw a diagram. Okay. So here you are standing on the surface of the Earth with your little GPS receiver. And let's just say, for example, you are standing next to a very tall building. Right, so here's you standing next to a building, and then up in the sky, just like before, right, we have a satellite broadcasting a signal down to you. So let's go ahead and walk through the possible places where this simple communication can go wrong, or some places where we might get information that is inaccurate. So the first thing we have to realize is that the satellite is in space, right? That's why this is called the space segment. And you're on Earth using your little smartphone or your tablet or whatever, which is why this is called the user segment, right? But something we haven't talked about is that there's this big area between you and the satellite, right? And in that area is called the atmosphere. Right? Hopefully this isn't a shocker to anybody. We have atmosphere that is between us and space, right? That's part of the reason why we're able to have breathable oxygen at the Earth's surface. That's partially why our planet isn't freezing cold or boiling lava hot, right? We have this atmosphere that performs all kinds of critical functions. But one of the things that it can do, right, is if we have a signal coming from the satellite, it hits the atmosphere, right, it can interact with the atmosphere. It can be diverted off, it can be absorbed in, right, it can be potentially slowed down, right? So the first source of air that we have are called atmospheric interactions. So let's go ahead and make a list over here called sources of error. Right, and our first error is going to be not T, it's going to be atmospheric interactions. Right, the idea that the signal is going to interact with the atmosphere, either be bounced off, absorbed into, or possibly slowed down. Right, so we have the atmosphere in between us and the satellite causing us problems. Okay, that's fine. Let's talk about what else can happen. Right, so in this case here, right, you're standing next to a building. And you have to realize that the signal the satellite is sending out, it's sending it out in all directions. Right, and so what can happen is, instead of hitting you, maybe the satellite hits the building, bounces off the building, and then hits you. Right, so this bounce off right here, right, we call this, let's use a different color for that. Right, we call this bouncing right here, this is a multipath error. Right, multipath error. Where you have the signal coming from the satellite interacting with things before it reaches you. So this could be a building, this could be a tree canopy, right? The idea is that the signal's bouncing around before it gets to you. Now think about what that's done, right? When the signal's bouncing around before it reaches you, right, the path of the signal from the satellite to you is no longer a perfectly straight communication. Meaning, right, that every time it bounces off, it's taking more and more time to reach you. Right, the satellite sent the signal at the same time in both of these cases, the direct case and the multipath case. But in the multipath case, right, it took longer to reach you, meaning that our assumption that range equals velocity times time, right, we've messed with that time a little bit. It's taken longer to reach us than it should have, meaning we're going to calculate our distance incorrectly. So the second thing we can have happen is what's called multipath errors. Okay, so the next thing that can happen, right, is that it's possible that maybe the satellite was wrong when it communicated its position, right? These position calculations are based on mathematical equations that are very, very accurate, but sometimes, right, they can be a little off. So what if the satellite is communicating as though it was here, but in actuality, let me do this in a slightly different color, right? But in actuality, maybe it's here, right? So this would be the actual position, right? And this would be the stated position. Right? And so if you remember back to the concept of trilateration, the idea was that we were using the distance from the satellite and the satellite's stated position as the center for that circle to figure out where the different satellites intersected. Well, what happens if one of the satellites or one or more of the satellites tells us the wrong position, right? What if it's broadcasting from here, saying it's here, all of a sudden, right, our circle is completely off, right? That idea that we have those spheres of intersection are off. So when the satellite tells you a position and the position is wrong, we call that ephemeris error. So ephemeris errors are, again, errors where the satellite is broadcasting its position, but it's broadcasting the wrong position, right? There's been some miscalculation, or the satellite has done something that it wasn't supposed to in its orbit, and so that it's telling us the wrong position. So for ephemeris errors, I'm going to say wrong satellite position. Okay? So we have the signal being corrupted by the atmosphere. We have the signal bouncing off of things before it reaches us, which increases the time it takes for the signal. And then we have the satellite basically giving us false data about where it is. Another error that we can have, similar to the position, is that we have what are called clock errors. Right, and basically a clock error is when the communication between the satellite and the receiver, there's a miscommunication in that time, right? The time that it was sent or the time that it was received. So basically with clock errors, right, we're mishandling that idea of time. So that calculation of how long it took the signal, right, it gets messed up because one side or the other is miscommunicating the time that it took to get to us. Therefore, we end up calculating that time part wrong. So with ephemeris data, we're calculating the position of the satellite wrong. With clock errors, we're calculating the time part wrong. So when we handle that equation, right, we're thinking that it took longer or shorter than it should have. So we end up getting a miscalculated answer. So 5, and this is the last one, is that, right, so the signal manages to get through the atmosphere okay. We're in good clear, we don't have buildings or anything nearby, so we get the signal from an accurate satellite traveling an accurate path to us. There's still another error that can go wrong, and this is called receiver noise. right? And so with receiver noise errors, what you have to think about is the fact that, as we mentioned in the previous video, right, this signal is traveling using electromagnetic radiation. And electromagnetic radiation involves light traveling at different wavelengths. And the receivers are set to pick up the specific wavelengths or frequencies that are being sent from the satellite. They're picking up those specific wavelengths, using those specific wavelengths to calculate all of the different pieces that are necessary to handle GPS. Well, here's the problem, right? Any electronic device produces some electromagnetic radiation just by virtue of it being on with electricity running through it. Okay? And so depending on the quality of your device, right, cheaper devices tend to have fewer regulations and tend to produce more of this excess electromagnetic radiation than high quality devices do. So in cheaper devices, in lower quality GPS devices, what can happen is you actually have the device itself producing some electromagnetic radiation at wavelengths that either are similar to or interfere with the wavelengths that are coming from the satellite. So the receiver is actually picking up its own signal to some extent, or it's producing radiation that interferes with the signal. And so what happens is the signal actually gets to you. The signal gets to you, but by the time that it does, you've actually got your little device here producing radiation that's either interfering with or being counted as data coming from the satellite. So the receiver itself is basically producing its own readings or interfering with the readings from the satellite. So even if you have a perfectly positioned satellite with a perfectly positioned communication system, there's no errors. These other 4 errors have all been minimized. The receiver itself is still kind of producing its own background radiation that can interfere. Okay? So, to recap, satellite emits the signal. The first thing that can happen is that it can be messed up in the atmosphere, either reflected, absorbed, or slowed down. It can hit other objects, so it can hit buildings and trees before it hits you. That's called a multipath error when it bounces off and hits you. The satellite itself may have inaccuracies in where it's located in terms of what it's communicating to you versus where it actually is. That's called ephemeris errors, when the satellite is communicating the wrong position. There can be issues in terms of the timing, in terms of the satellite maybe is reporting the wrong time, or the user has an error on their device that's causing the time to be misinterpreted. So you can have what are called clock errors. And then finally, if everything else goes right, you still have the receiver, especially lower quality receivers, actually producing their own radiation that either interferes with or is detected as signal, which can cause slight errors as well. So these 5 things are the primary sources of error in GPS. What I want to do in the next video is talk about something called differential correction that allows us to be able to account for most of these errors by using the other segment that we haven't really talked about, which is the control segment or the base station segment. So hopefully that makes sense. And as always, if you have any issues, please reach out. Thank you.